So number 5 is another one of the separation of variables. And I think y'all probably don't have too much trouble with these if I'm guessing, but let's run through one anyway. The first thing I'll do is rewrite that y prime as dy dx. And I want to get all the y's on one side. Let me go ahead and just make this a proportion by drawing that, big long fraction bar and then sticking this over 1. When I first start out, it doesn't look so nice. You get 3y dx is 2 plus x dy. Everything's not where you'd like for it to be. And what happens, one of the big ideas in this section is you're dealing with your log function, which is most of the time going to be natural log. So you can see how that is going to happen on these problems, because if I want to get the x's over with the dx, I'm going to have to divide both sides by 2 plus x. That'll get it off of that side, but put it over here. But I also want to move the y's over with the dy, right? So I'm going to do it on the same step, but I'll show it in a different color. So I'm going to divide the y's off of this side to get rid of them, and they'll end up over here. Well, if you look what you have, once you kind of do that moving stuff over with the right variable, you have, and I'm going to write it a certain way so that you notice it is going to be a log function. I have 1 over, isn't 2 plus x the same thing as x plus 2? I'm just going to write it that way. 1 over x plus 2 dx. And over here I have, I don't know why I put that integral on there. I was just trying to simplify, but I'm going to integrate it next. Over here I would have 1 over 3y dy, but the next step is to integrate each side, right? Okay, now they do some weird things in the answer key. So I would check my answer and I'm like, how'd that 3 end up over there? I don't understand why, but one of the things I just already realized that I did that's not going to match up with the answer key is we're going to have natural logs on both sides, but they try to make one of them nasty and the other one really clean. I don't know why, but here's what they did, so let me go ahead and do it. This 3 here, they actually just, in the answer key, they moved the y over, but they left the 3, so here's, and let me do it the way they do it just in case you go look it up so you'll understand some of what they're doing if it differs from your work. I'm going to multiply both sides by 3 just to get the 3 back over there because I forgot. Because, again, that was not my natural inclination. My natural inclination was to move it all over. So they have 3 times 1 over x plus 2 dx equal, and over here it would just be 1 over y dy. So there's some funky stuff going on. So now what we had was 3, I'm just going to rewrite this so I'm going to be looking a lot over here just because my natural inclination is not to do what they do. This would be 3 ln absolute value of x plus 2, and remember the absolute value is just saying that I can't have a negative, I can't take the log of a negative number. So that's all that x plus 2 is there. Anytime you do an ln, you need to stick those on there. And then plus c. In the answer key, they're going to call that C1 because they change the C's sometimes 2, 3, 4 times in a problem. So they're just kind of saying, okay, this one's different than that one, but it's okay, we can still call it C, Over here, we just got ln y. They'll usually put the C, when they integrate, they'll put the constant again with the x side, just kind of like I talked about a little earlier. So I've got this. I want to solve for y, though. I'd like to have y equal something, okay? Now, if I'm going to do this, okay, here's where it starts getting, you got to remember those rules of exponents. One of the things they're going to do, that hurts my ears, one of the things they're going to do is move that 3 up there, use the law of exponents to get rid of it. That's one of the reasons they actually put it on that side, and that's one of the reasons I moved it, because this is what you'd see in the answer book. I know, that was doing it earlier too, and it just bothers my eardrum. I don't know why. Yeah, it's that deep. Yeah. In addition, they also do this. Never would have thought to do this either. If I have a constant C1, I could say that, I could just lump it in with another, I could call it LNC2 and make my constant fit into that scenario, basically. And the reason they do that is because when they go to simplify it, the answer's going to look a little cleaner. It's kind of like that art versus, artistically trying to get through and have a nice looking solution versus flogging it to death, I guess. But I would never have thought to do these things myself, okay? So what you end up doing now is we need to solve this for y. So we're going to take both sides and we're going to, basically, oh, well, that's that whole thing. Sorry, I got off a little bit. This whole side, and we're going to have e, and use these as equal exponents, and we end up with x plus 2 cubed. Okay, this is where it also gets really weird. If I have two exponents, and remember, logs are really exponents. It's multiplying. So what they do is they put their c out front. Because now that they've made this an ln, you have, an ln of something plus the ln of something else. We can multiply those two. So they just say, okay, the ln's are going to kind of cancel out, and this is going to become c times x plus 2 cubed. Which, again, I wouldn't have really thought of that, doing all that, but my answer didn't match up, so I was trying to figure out, well, okay, what did they do here? So this is basically the answer right here. They just they end up, I think, writing the y on the left-hand side. Is that really somebody's stereo?
I think it's a truck. No, like a diesel.
Okay, just sitting out there. Okay. So anyway, that's where they get their solution. So they do a lot of things with these exponents. So if you go and you look and your answer doesn't match up, see if they've done something with including this c into that natural log term, because that would be easier, I guess. If you were to be given an initial value, you could stick it in there. If you were given a point, you could solve for c really easily. So there's some advantages to writing it that way. Okay, so this is problem number 29, and the directions say determine whether the function is homogeneous, and if it is, determine its degree. Okay, a homogeneous function is a function where, a function is homogeneous if you can kind of rewrite it. Let me kind of explain why you need it. You need it for functions that aren't easily differentiable. If you look at this thing, you've got x squared plus y squared underneath the radical. And if you're trying to even look at that as some kind of ln function, you do not have the derivative of either one of those things is not the derivative of the other. So we don't really have methods to differentiate this yet, but we can tell whether we could differentiate it. That's what this whole idea of homogeneous function is. Is there a way that we could differentiate it? We may not know it yet. We might learn it in Cal 2 or Cal 3, but we can determine now whether it is able to be differentiated, because you can't differentiate just everything. So here's what you do. First of all, let's look at some of the notation here as we kind of discuss this problem. If you had f of x, that would mean you have an x and a y, right, in your equation. F of x is usually just short for y, isn't it? And so you got two variables, a y and an x. This book is called Single Variable Calculus, I think. Oh, actually, it has everything in it. We're focused. One of the reasons we kind of skip some sections and we skip some problems is that we're focusing on single variable calculus, which is what you usually do in an AB class. So you can stand up and do some stretches.
I was paying attention, and then
is it lulling in your brain?
It's lulling me out.
Yeah, it's kind of hard. So when we have f of x, y, that means that we actually have three variables here. We're not going to mess with all three of them. That we have almost like, you could look at it as you got two input variables, and you might want to call f of x, y, z or something, okay? We're not going to learn how to differentiate this in this class. That's way beyond the scope of this class. But if we can determine that it's homogeneous, then we can say, yes, it could be differentiated. And here's what you're looking for. There's a theorem on page 424, and explains what homogeneous is. It says if if you can write, okay, so if it's homogeneous, you can rewrite this function like as a multiple of something. For instance, I can take and say, all right, I'm going to multiply my x and my y by some term t, and I don't really know if t is a number or t might be another function, but I'm going to multiply through by t, whatever that is. It will be differentiable if when I get done, let me draw a line over here, if I can factor t to some power out of my original function, if my answer looks like this, the original function times t to some power. So in my answer, I want to see this. I'm going to go over on time. I want to see this, but I want to be able to factor t to some power. It can be t to the first power or whatever, but out front of it, I need to see that. Okay, so what I'm going to do is I'm going to come over here to determine if this is homogeneous, if this is able to be factored. I'm going to replace x squared with tx and square that. I'm going to take that, replace y with ty squared. You're just multiplying through by something. And then on the bottom, it would be square root of tx squared plus ty squared.